Black holes are often described as some of the simplest objects in the universe because from the outside, classical physics only needs a few properties to describe them: mass, spin, and charge. But the moment a black hole is born is not simple at all. When matter collapses under its own gravity, space-time begins to behave in extreme ways, and near the final threshold, something strange can happen. A system can come incredibly close to forming a black hole, but still not quite cross the line. This knife-edge region is known as critical collapse. For decades, physicists have known that critical collapse is not random. In the 1990s, Matthew Choptuik showed through numerical work that collapsing systems near the black hole threshold can repeat themselves at smaller and smaller scales, almost like an echo in space-time. The pattern is called discrete self-similarity, which sounds technical, but the idea is surprisingly elegant. As collapse approaches the decisive point, the geometry appears to replay a similar structure again and again, each time on a smaller scale. It is not chaos, it is organized collapse. A recent Physical Review Letters paper by Christian Ecker, Florian Ecker, and Daniel Grumiller gives this old problem a new analytic handle. Instead of trying to solve the full four-dimensional problem directly, they study gravity in the large D limit, where D means the number of space-time dimensions. That does not mean our universe has hundreds of visible dimensions. It means the researchers use a mathematical tool. By looking at gravity in very large numbers of dimensions, the equations become easier to control, and patterns that are almost impossible to see directly can become clearer. The result is an infinite family of analytic solutions for Einstein gravity coupled to a massless scalar field. In simpler terms, they find a controlled way to describe a collapsing system that repeats itself in time and scale. The repeating structure is not just a visual curiosity. It may tell us something deeper about the transition between ordinary matter dispersing away and gravity becoming strong enough to form a black hole. One of the most fascinating ideas in the paper is the self-similar horizon. This is not the same as the event horizon of a finished black hole. It belongs to the critical solution itself, the strange transitional spacetime that exists at the edge of collapse. In this regime, spacetime can behave almost like a crystal. Not a crystal made of atoms, but a pattern that repeats in a precise, discrete way. A spacetime crystal. That image is powerful because it suggests that black hole formation may not be a smooth fall into darkness. Near the threshold, collapse may pass through a highly structured phase where matter, geometry, and scale become locked into a repeating pattern. This does not mean the new paper proves an alternative theory of black holes. It does not prove fuzzballs. It does not prove any specific quantum gravity model. And it does not directly describe real astrophysical black holes in our four-dimensional universe. Its strength is more careful than that. It gives theorists an analytic window into a phenomenon that was mostly understood through numerical simulations. And that matters, because analytic control helps physicists ask better questions. If collapse organizes itself before a black hole forms, then maybe black holes should not be thought of only as final objects. Maybe they should also be understood as processes, transitions, dynamical pathways into an extreme strong field regime. This is where the idea becomes especially interesting. Classical general relativity tells us that black holes have horizons and singularities, but many physicists suspect that this cannot be the full story, because quantum gravity should become important in the deepest strong field regions. Some approaches, such as fuzzball ideas, suggest that the endpoint may not be an empty classical interior, but a structured, information-carrying state. Other speculative frameworks try to describe strong gravity in terms of organized vacuum behavior or coarse-grained coherence. These ideas should not be confused with the PRL result. The new paper is about critical collapse. It studies the route toward black hole formation. But conceptually, the connection is tempting. If the road into a black hole is already structured, then perhaps the object that emerges is not completely featureless either. This remains speculation, but it points toward a broader question. Are black holes truly simple objects, or are they the visible edge of a much deeper structure? The careful conclusion is that this new work does not solve black hole physics. It does something more precise. It shows that critical collapse can be studied analytically in a controlled approximation, and that the threshold of black hole formation may contain repeating, organized structure. That is already important, because black holes are not only destinations, they are events, they are transitions, they are the universe reorganizing spacetime under the most extreme conditions we know. And perhaps, at the deepest level, the birth of a black hole is not simply matter disappearing into darkness. Perhaps it is spacetime finding a pattern before the horizon closes.